This is a multi-subcase loading in MSC Nastran. In the subcase 1, we are applying pressure here. So this is the animation we got. And in the bending, in the second subcase, we are applying the load in between and we are fixing the ends. So let's see how to do it. So I will just import the deck which is used in the previous video first. So I don't need to define the uh, properties again. And the element definition is already done in this deck. Now I'll just delete this RBE2. I don't want in this deck. Now just let me just delete the empty collectors. So this RBE2 doesn't contain any element in this collector, so I can just delete this. Now suppose I need to compress this bar and I'm applying 10 MPa pressure in this direction, pressure, and this face is fixed. So how to do it? So as you can see, some SPCs have been defined. I will just switch this on the SPCs, and here nothing is defined. So you can see this SPC is constrained in 1 2 3 directions as it is a solid element, so no need to constrain 4 5 6. Now pressure, I don't even need to define the direction because pressure will always be uh, negative of the normal. So the normal is pointing in this direction, the pressure will be applied in this, and we will just go to load. See, before that I just need to create one more collector here, load collector. So I'll just put here pressure. Okay, now I'll just go on here and just uh, click on here where there is a pressure symbol, and then I'll it is set to, there are many payloads here. So basically
So
most old card is the payload card, which is like the uniform pressure, but it can only be applied to 2D cell surfaces like the 2D elements like quad and tria, and where pressure will be applied to the normal of the face. Second is the payload 1 card. Payload 1 card is basically used for beam elements or bar kind of 1D elements where we apply pressure to the uh, length of the element and where the pressure can even vary between 2 points. So at one, in the single bar element at one point I'm applying the pressure, suppose 2 newtons, 2 MPa. Other point I can apply at 3 MPa and it can linearly vary. Now payload 2 card is like a payload card, but in payload card we are defining the pressure as per the grid points, as per the phase defined by the grid point. And in payload 2 card we are applying the pressure as per the element phase. Both works the same, and you can even, wherever you are using payload 2 you can use payload, and wherever you are using payload you can use payload 2. But for most cases these cards are never used. Mostly payload 4 card is used in most of the cases as in most modern type of pressure card, which can be applied to cells and solid, and for most of the cases we will be using payload 4 card only. Now we have understand that payload 4 is the most generalized one, and it will be used mostly in almost all structural analysis due to its simplicity. So we will use payload 4, and we will just select these elements. Once this element has been selected, we'll just go on here and constant vectors, for example, and then we will just type 10 here, and we'll just say create. Okay, So there are some payloads we don't even want it like in this direction, in periphery direction. So what we can just type L loads and we can just start delete these loads. So these loads are deleted and you can see that pressure is applied only in this phase of 10 MPa. So this subcase I will again rename this pressure 10 MPa, and SPC is already defined. Loads I will define it as this load collector. Done. So if you see here in this subcase, this phase is fixed, and here I am compressing this via pressure. Now within the same BDF file, I need to solve one more subcase. So I'll just go on here and duplicate this, and this pressure I will just go on here and type bending, and secondly this pressure, this SPC, I'll just go on here and type duplicate here, and SPC for bending I will just give rename it here. And if you see here, this SPC doesn't contain anything, so I'll just go on here and constrain this both ends again. So here for bending I'll just go on here and fix this both ends, and I will apply the load in the exactly in the midspan. So for this I'll just switch it off 456 as I don't even need it. Even if I use it, there will not be any issue. Just go on notes here. This face we have selected, and also we will select this face also. Done. Create. So as you can see, these two faces are SPC for bending. Now we will just create one more load collector, load for bending, that is around 10 kilonewton. We need to apply it here. So I just need roughly the midspan. So what I can do here is I can just go on, press F8, create free nodes here. Just go on here, and so this is just nearly in the middle. So I can just clear this nodes and just go on to here, uh, analyze loads. Just click all these nodes. So you can see all these face nodes are selected, and it is, I want to apply 10 kilonewton in the in the mid span, and I have 108 nodes. So what I can do here is I can just go on here and type components. Now I need to apply in the negative of in the positive of y. So I'll just put here 0 the 92.593 approximately, and we will just create it. So you can see that this loads have been created. Now we can just switch it off and switch this off also. Just switch it on for both for time being. And now we can go to our load case again. This is this second is bending, and we will just click on SPC and choose this SPC instead of one. And instead of pressure, we will just choose this pressure and this uh, load for bending. That's it. So just let me hide all this. Go to feature line view, then go on here and pressure and just type Q here. So it will review this. So as you can see here, it is 1 2 3 is constrained in this end, and this end uh, pressure of 10 MPa has been applied. Just press Q again, it will go back to normal. Go back to bending here and type Q. So it will review this load collector. 1 2 3 here is constrained. 1 2 3 here is also constrained, and a load of 92.6 newtons have been applied in this node, and there are 108 nodes which corresponds to around 10 kilonewton of load. Once this is done, type press Q again, then just go on here and export this deck. So 101 subcase 2, and just click all and just export this. So this OP2 has been generated and it is solved. We can just go on here and verify this. So this linear static analysis has been completed, and just go on here and open F06 file. So you can see here, you can search for fatal. So there are no fatal found in the entire column, so you can just close this. So I have just opened the OP2 file, and now you can see the now there are two subcases that we have solved, the two subcases, pressure subcase and the bending subcase. So first we will review the results of pressure 10 MPa subcase. This case we are constraining it here and we are applying the pressure of 10 MPa. So we will first see the animation. So just I'll put it as 100 as 1000 to make it more visible. So you can see that this is deforming in this direction, and just I'll put as 1 now and stop the animation and check our stresses. So we have applied the pressure in this phase. So sigma zz must be dominant, and it should be nearly equal to the same pressure value which we applied, which happens to be uh, 10 MPa. So it is 10 MPa here. So now we can also check the SPC force, whether the pressure is applied correctly or not. So you can. So I'll go to plots here. Sorry, plots here, and just go on here and uh, do this. Do by plane. Just just click on here to z-axis, and tolerance will be 0.1, and it's in z-axis plane, it's in xy plane, so I will put z-axis, and base point I can just sorry, base point I can just select any base point here and just click on add, and that's it, apply. So a new window has been opened, just click on here and just export. Just go on and export this curves. So this has been exported. Now we can just go on and just click on this to find out this sum as 190,1991.107 newtons, pressure as 10 MPa, and the area of this is 199.11, so which happens to be the same, approximately the same value. That means the SPC force, summation of SPC force is matching with the whatever the load, external load we applied. So now just go on here and I will select this bending simulation, and now I'll just go on and switch on the animation. As you can see that uh, it is sagging in the positive y direction. So that means we have constrained this end and this end. Now it's exactly like a fixed beam. So we can just go on here and calculate the displacement also. So just go on to displacement, and the dominant one is the y direction. So I'll just go on and plot the y direction displacement. As you can see that it is approximately, if I'm not wrong, it is approximately, just switch on the max displacement, sorry. So it is approximately 78.625 mm of displacement, which is exactly at the center. And this happens to be the case of fixed beam where both ends are fixed and load is applied at the midspan. So its maximum displacement theoretically is PL cube divided by 192 EI. So this, if we calculate it like this, it happens to be approximately same value. So now we can just go on here and plot the SPC force along y direction. And after plotting, we come to see like at fixed location, the SPC forces values are there. So we just go on here and we will just add it up. Just go to this plots and select this second subcase and SPC force, and in y direction you select this subcase, and now just click on this and do it via plane, and we want it in xy plane, so we will go to z axis. Now base point will be this one. Base point will be, and again we will just select this nodes also and just click on apply, and just go to the new window, and here these are plotted, so we will just maximize this, and then we can just go on here and export this. Just click on this current plot and export this. Once this is exported, just open this. So if you just go on here and see the sum, it's coming out to be 10,000 Newton, which is nothing but 10 kilonewton. That is the force we applied.